Thank you for your presentation. I'm going to present you the part of my thesis work called closed loop system identification using a Verlet PI controller and reference prefiltering. We are in a white noise case. And this work, my thesis work, is a collaboration between two laboratories. The first one, IMS, with the identification and automatic skills, and I2M, I2M, the mechanical laboratory, which they are focused on the machining. And I'm working with a company called the Verlet Robotics that brings the skills about the robotics and machine tool. So, just before I'm going to present you the context of the thesis and this work. Then I will talk about the problem formulation and all the system identification that I will present you. So the least square, the extended instrumental variable, and simplify the refined instrumental variable methods. And then I will apply them to a simulated system. And I will conclude and talk about some future work about this system identification. So first, the context. I'm working on the machining and how to minimize in real time the energy, mechanical energy consumed during this machine, this process. Why? Because it's improve. That's improve the workpiece quality, reduce the residual stresses. That's improve the fatigue of the workpiece, and enhance the ecological sustainability. In my thesis, I will work mostly in the milling part, not all the machining. So just before, I have to model about the forces and moments around the tooth, cutting tooth. Let me compute the energy, the mechanical energy. Then I can optimize this energy and I can do the feedback around the forces and moments optimal one. And I will and then I can implement a robust controller. Then I can send control signal as a torque for the spindle motor and the machining process. So this spindle motor is the main actuator on this system, and this is why I want to identify this system. So the spindle is here in inside a 3-axis machine tool. And what is a machine spindle? So a spindle is a motor that can drive a cutting tool, such the milling tool or a drill tool, at a specific speed. In our case, where we are using the machine tool called DMG represented just there, which is inside the spindle that I will present you just after. This machine tool is the computer numerical controller called CNC by Siemens Numeric. What is a CNC? So the CNC is a main interface for in the machine tool that gather all the data, all the recording data in one interface, and can send different commands, different control in the different actuator. We have some pictures about this software environment. First of all, we have the two first photos that show the recording of the data, and then the other one, the coding to how to implement the desired tool speed of for the spindle motor. And then we have the spindle motor inline master that's of the machine tool, and it can go to 15,000 rotations per second per minute. Sorry, and it's an electro spindle. So this system is already in a closed loop made by a Siemens designer. I found some documentation. It was quite hard to know how is the structure of this closed loop, but this is what I found. And this closed loop bring a parallel PI controller and a prefilter for the reference just set for the integral controller. And we have some different signals. First of all, we have the reference, which is the desired angular speed, the control, which is the torque, the measured, which is obviously the angular speed, and an external control, which is called anticipated torque control. And this one cannot be handled by the user, and it's just directly controlled only by the Siemens device, where I can't control them.
So, Jamy, that means you cannot excite. It's excited, but you cannot.
Yes,
you cannot
exactly.
choose the excitation.
Exactly.
Okay. Yeah.
Just with a few amplitudes. In fact, it's not so high.
Okay.
And the system to identify consists of the electrical currents controller, the spindle motor, of course, and the sensor, the rotary encoder. So we suppose that the system is linear time variant around the working point, a singular input, single output, stable and vitiated by a white noise. And we can summarize this big previous block diagram by this one, where we found the reference signal as R2, the external control as R1, the measured output Y control signal U, and the noise, white noise, E0, and the true signal system G0, and CP and CI, respectively the proportional and integrator controller, and the reference prefilter denoted by F. First of all, we want that R1 and R2 should be persistently exciting. And thanks to the parallel PI, we can have the R2 is not filtered by the controller, because we have the proportional one that not filter the signal in the control signal. So the aim of this presentation is to explore the closed loop system identification methods in white noise case.
And why do you choose white noise? Because it's a sort of, is it because a perturbation which is white, that is sort of a vision of the spirit. It's generally not white.
Yes, absolutely.
So, but why you suppose here that it's white?
First of all, we tried with with white noise, and
Okay.
then we go to the colored.
First step. Okay.
It's in a perspective.
As Marco said, this is for the next slide.
So, but you prefer that the question comes later, just say it, because since
No
I'm
problem.
getting tired, and I ask directly.
So we are in the white noise case, and we have obviously with reference prefiltering and the parallel controller. We are in the discrete time case 2, and we want to make a Monte Carlo simulation to analyze statistically, the proposed method in this presentation. So about the problem formulation, as I said, we have two controllers, proportional one, integral one, with a prefilter denoted by F. We express all of the external signals as R. That depends on the external control and the reference, which is filtered by the controller and the prefilter. And then we have the signals of the input and the output of the model, the system. Y is depending on, of course, the system and the control signal and the measured weight noise. And U is depending on the external signals and the feedback of the measured output. So the objective of this system identification is to find the parameter vector theta that depends on the coefficients of the model transfer function, and where the coefficient NA and NB are the degree of the polynomials A and B. And NK is the system delay assumed known. Of course, we suppose that the model system is in the same class as the true one. So, about the system identification method, I'm starting with the least squared method. First of all, we have to minimize the quadratic criterion that depends on the difference of the measured outputs and the estimated output y hats, which one depends on the estimated coefficient and the path of the measured outputs and the path of the control signals, which one depends on the external signals and the feedback measured outputs. This difference is filtered by the state variable filter called FSVF. And this one, in our case, we choose that it's a Poisson filter expressed in discrete time, where the omega c is the cutoff frequency of the filter, Ts is the sampling time, and Na is the degree of the estimated denominator of the model. And this algorithm is a direct method. I did a scheme that represents all the algorithm of this least square method. First of all, we are doing the signals generation with the red boxes that using the external inputs and the visual outputs to get the the control signal. And then we are filtering the control and the outputs to get what UF and YF to gather this signal in a regular vector then a matrix, and we can compute the estimated parameter vector called theta ls. Then I will talk about the instrumental variable, extended instrumental variable. This method has to minimize the criterion. It's quite the same as previous. However, we find a new data called Z. It's the instrumental vector, which gather all the instrumental variable of the control called new, which depends on the external inputs only, and the previous estimated model, and X, which is which depends on the instrumental variable control and the previous estimated model. So I said it's we are using the previous model. So of course this model system, this method is obviously iterative. This algorithm is quite the same in the right hand, but in the left part, we will find the instrumental variable system of the system. So nu and x that gather on the instrumental vector, then a matrix. Then we can compute the new parameter vector, which can be used on the next estimated model. This method can be stopped by the criterion, which is set to the sum of relative difference of the parameter vector. And we can use a different type of initial parameter vector, just above, and we can use, for example, the parameter vector just found in the previous method with the least square method. And about the simplified, refined instrumental variable method, the criterion is quite the same of the last one. However, the filter is not the seed variable filter as we can see with the Poisson filter. We are using an optimal filter. Where we can find this? This one depends on the error function, which is depending on the measured output and the estimated one. And we can factorize by the inverse of the denominator of the model. And we can come down to the filtered equation error, where the new signals are set to are filtered by the inverse of the denominator. And in our algorithm, we can set this optimal filter as the previous denominator found by in the previous iterative loop. So this algorithm is quite the same. However, in the prefiltering data in orange parts, orange boxes, they depend on the previous parameter vector found in the previous the initial parameter vector can be used randomly, or we can use the previous the parameter vector in the previous method too, with the IV method. And then about the I will talk about the application about all those methods. Just before we set the simulated model as this equation. So this transfer function is an order 2 with one sample delay. We can find the cutoff frequency around 30 radian per second. We set the sampling time to 5 milliseconds, and we choose the proportional and integrator controller like this, and the prefilter like that. Why we choose this prefilter? In the case of the machine tool, the reference prefilter is set as the closed loop of the system. In the case we have just the proportional controller without the integrator. And then we apply a Monte Carlo with 500 runs with a different SNR to 10 from 10 to 20 dB. R1 is not handled, so we set to 0. R2 is a pseudo-random binary sequence with 4088 samples, which gives us a simulation of 20 seconds. And the order of the system is supposed known. And as I said previously, the external input R is sufficiently persistent because of I2 is not prefiltered by the proportional controller. So, about the results, we choose for this identification a Poisson filter, state variable filter, as omega c equal to 60 radian per second and an order to 3, which chose this cutoff frequency by trial and error and found a better result with 60 radian per second. We tried, of course, the classical methods with simplified, refined instrumental variable, but without including the parallel controller and the prefiltering. It's the same for the instrumental variable, and they didn't converge.
What do you mean by they didn't converge?
That didn't give any value because they the instrumental variable we have to find it's a loop. So if the parameter vector don't go to the right parameter, the instrumental variable we found some unstable coefficient and won't converge at all. And I don't know if you can see rightly, but we have the three frequency response with the least square extended instrumental variable and the real-fine incidental variable. The first one, the least square, we can see easily that we have a bias, and it's shown very easily in the low frequency. However, to see better, I plot all the coefficients with the different methods according to the number of realization of the Monte Carlo, and we can see the bias of the least square method. And the extended and the simplified, refined, and incidental variable are really in the same. I don't think you can see that it's very centered by in the true variable, true parameter. However, if I'm interested in the about the standard deviation, we can see the simplified, refined instrumental variable are quite better about this than the instrumental variable. For example, this 1, 5, then 7, etc., etc., where the standard deviation of each parameter are better in the simplified, refined instrumental variable. So, to conclude about this presentation, I presented some extended algorithm, such the least square extended instrumental variable and the simplified refined instrumental variable, which are evaluated in the closed loop with a parallel PI and a prefiltered reference. The closed loop refined simplified refined instrumental variable methods ensure that we have a consistent estimates. So we have the better standard deviation, and we are not biased. And for the future work, I will apply these methods. They simplify refined instrumental variable on the real machine tool to identify the spindle system around the different operating points. And I will extend to the system identification with a colored noise case. Just after, with this system identification, I will design a robust control to minimize the power consumption during the machining. So, thank you.
Thank you, Jamy. So it's nice we can have a long discussion, 15 minutes for questions. But that's good. That's the purpose. Can I start? Because can you go back to, well, where you have the, the loop is presented, just because you say, well, no, the loop, the system you want to identify.
Okay.
No, not the, where there is G0 in it and no white noise.
Okay.
Yeah, that guy. Okay, well, so you chose 3 methods, so, but when I see that, why I didn't try output error method? That's my first question.
Okay. First of all, we have a control which is already vitiated by the.
No. Output error method is you type YU, you take a U and Y, and you just use OE in MATLAB.
Sorry.
Because in fact, just to tell you, in system identification and closed loop has been studied, and when you are using the direct method with U and Y, you know that you have to use a full order model structure both for G and for H. H is the noise model. So that means you need to have to choose a 0 equal to 1. So that's basically what you do with output error method. That's the prediction error you will minimize, whose power you will minimize, is y minus g theta u.
Okay.
And there you know that you will be consistent. Well, of course, you have to initialize with a good theta zero, but it's a nonlinear optimization. But you know you are consistent, and that will be the minimal variance estimate. And because you discuss also about the informativity, and well, you say that R1 and R2 they are not so informative, but you chose R2 as a PRBS,
Yes.
so that's quite informative. So it's white noise. But in fact, with white noise, you are in a situation where you can put R2 and R1 equal to 0, and you still have a consistent estimate if you use U and Y, and because when it's white noise, the feedback of the noise excites efficiently. But that's why I asked you. Yeah, if your noise is not Y, then well, that's not true, effectively.
Yeah, okay.
So yeah, my question is, have you compared it with output error approach, where output error approach is the sort of the minimal variance approach for that type of problems?
Not really, because not really. I didn't try to with just an output error.
Yeah. Because the least square, that's supposing that your noise models is 1 over the denominator of your numerator of your G.
Yeah.
And so there it's not good. Then well, even in open loop you're screwed with an ARX model. So yeah, I would advise you just to try output error method, and also try with R2 is equal to 0. So you will see there you get already a consistent estimate if you have enough data. Well, a consistent estimate is when n goes to infinity.
Do with R1 equal to 0.
And R2 also.
In a real with a machine tool, I won't be able to.
No, well, whatever R2, if there is a R2, then you get smaller variance. That's what's good. But even if R2 is 0, you get already a consistent estimate in this. Well, if your noise is really wide, so
Our context is still the machining tool, so you have to identify the system at different operating conditions.
Yeah. And but then you will take a U and Y at different operating condition, and so.
Okay, but you have to bring the system at this operating system.
Well, maybe, but that's here. But with all methods there also, I guess. So R1 and R2, that's just around the set point. You have certainly R2, which gives you a set point, and then you excite around it. But you even don't need to excite. It can be just, and then it's not U and Y, it's delta U and delta Y with respect to the U and Y at the set point. But I guess,
we can try.
Absolutely.
You can look at the classical result in system identification, and for this informativity results, that I guess you can look at sort of in closed loop. That's something we wrote with Michel Gevers as well. It's a result of Michel more than I am a co-author of that, but I can send you this reference. So now.
The thing is that we know that in the real machine tool we have color noise, so we wanted first to do it step by step. With this simple case, white noise.
Yeah, but if there is color noise, then you can use Book-Jenkins, and that will be the only method. Well, IV method will always work, but then if you don't use optimal IV, well, then you'll have a variance which is higher than with Book-Jenkins. So
on top of that, I think that the initialization of time might be
that's IV.
You use.
Yeah.
But I'm the one who wanted him to work on IV methods.
But IV it's good for initialization, but sort of then you can use a more optimal, sort of not optimal in the sense it's the best method, just optimal to reduce the noise effects on your estimate. So other questions? So I don't want to monopolize the.
What is because you had many huge acronyms.
Yes.
So what is the FR at the end?
For the filtered reference.
Okay.
Yes, it was a good one.
Yeah, what I mean is that you've got huge acronyms,
Yes.
and in the end, you don't use them because they're too complicated.
Yes.
That's like everything, no?
And why is called a state variable filter? Because there is no state there. I thought. And why there is a filter, basically? Why there is a filter? Why is state variable filter?
About the filter, it's how can I say? Okay, we are with a white noise case, and we say exciting all the frequencies, but I don't want to identify the high frequencies with because that will be just purely noisy and not without any signal, real signal. So that's the reason why I put the cutoff frequency just after.
So it's a low-pass filter, basically.
Yes, yeah, absolutely, absolutely.
Yeah, okay. Yeah, that's sort of reducing the bias of your least square estimate. That's the goal. Somehow,
it's supposed to not really to reduce the bias, but to lower the standard deviation.
Yeah, but okay, but then you. But anyway, you have a bias. So what's the so? But because in fact, if you use output error, you don't need pre-filtering. Yeah, sort of in the it's of course with real data we can always do a little bit pre-filtering. It's maybe good, but here it's just simulation on a linear system. So so I guess yeah. Why? Yeah, sort of removing information. I am trying to understand if it's because when you use a RX model, you have a bias, and so is this filtering to remove that bias somehow? No, maybe the sort of if I remember well. So, but we'll look at it because here I'm a little bit too tired. So
when we use a pass filter, is just to remove the noise so that your it's more effective in the instrumental variable because you will get thanks to the instrumental variable you will get well, you remove the noise effect and it removes the bias. In the discourse, it won't be efficient enough, but it will remove some noise.
Yeah. Okay.
In any case, when you're using the discourse, you know that when you have a high noise, it will be biased. The estimate will be biased. But it's a good fit to initialize the other methods. So, for example, the external instrumental variable or the optimal instrumental variable method.
Okay.
Now, the question about the goal of your work and what you're going to do the next step. So this is an identification process. It's a real-time identification process, if I understood. But in practice, the machine piece is going to write something.
Yes, absolutely.
So you will have 10 seconds the talk, something like this. Or you're going to do like identification or calibrate your model, or are you going to take into account a model of deformation or something?
During my meeting, I won't take into account the information that I will just take into account the efforts. And during for the about the speed, I can know it, but if I understood well, I'm not sure. You're asking me if the tool is in the same speed of the spindle?
The model that you have identified,
Yes.
are you going to use the same? Are you going to really identify again a model that
Okay. For the moment, I will use the same model at the beginning, and we can go to the online if we can if we're saying it's not it's depending of the material, but in fact it's not. We tried with two different materials, sorry, and it's quite the same response, frequency response.
Well, the system can change a little bit if you're looking at different open endpoints. But the thing is that we need some model of frequency responses to design the robust control. So we'll have a robust control. So it will take into account the uncertainty of the system, which will be better than the PI controller that is already injected now. But the first aim is first get the knowledge of the system, so system identification closed loop, then design robust control, and third part, minimizing the energy during the process.
But is it possible to remove the PI controller and put your own controller?
Although no, but we have to design another control loop to because we can remove the PI controller, but there is no interface for the moment to put the robust controller. Okay, so that's the work with DRM Robotics, the company where we are working on to design, let's say, another embedded system to inject
the question is, if ever you need to move and put something aside, it would be an idea to try and identify the single system without the PI controller.
Okay.
So, from the outside, that's what comes to my mind. I mean, you could have removed the PI controller, just identify the system, for example, with a proportional known value of the peak controller, and then just get an image of what.
At the beginning of the talk, Jamy said that we are not able to remove for the moment the PI controller. But so we cannot excite that with R1, the external signal. Okay. And the following we are still talking with Siemens to be able to inject directly with R1. But for the moment it's still it's sterile.
Interesting.
So that's the part of DRM Robotics who know how to design the control loop outside of the Siemens software.
Other questions? If not, let's thank Jamy once again.